So I am Sam Naffziger from AMD, a corporate fellow and product technology architect, and I get to talk to you today about some of the innovations required for the future of computing, which is quite an exciting landscape. So I'm going to start with some of the trends that are driving the demand for compute, and then go into the technologies required to meet that demand. And no surprise to this group, the growth over time has been dramatic in our industry, starting with the PC era and moving into smartphones, IoT devices, Internet of Things, and countless wireless devices, some of them embedded in our clothes and all through our cars and electronic devices, driving a huge explosion in the demand for compute. High-performance compute, as the data generated by these devices has to be processed and turned into something useful that makes our lives better. That processing requires computation, and it requires bandwidth, and the interconnectivity and the data generated all are causing an explosion in this demand for compute. So we really are moving into a new era. And the HPC, kind of the legacy high-performance scientific computing, is still a good example of the fast pace of this growth. This chart from the top 500 supercomputers is showing the top performance of the supercomputer installations over time. That's been growing at a doubling rate of once every 1.2 years, which clearly is faster than even Moore's law in its legacy instantiation. So this performance is driven not just by silicon gains, but by system-level innovations and architecture improvements. Now, the desire for higher performance supercomputers isn't just bragging rights on the top 500 list, but it's driving very real improvements in people's lives, solving problems that are pressing for humanity, things like new drug discovery, new energy exploration, and climate modeling, of course. And as all of us know in the compute industry, getting the next generation high-performance device is great for a brief period of time, but it really just whets our appetite for the next level of capability that we can squeeze out of even a higher performing compute system. So it's this treadmill of higher performance demand. Another example of that demand is in the gaming space. So here we've plotted GPU flops over time, which is a simplified but relevant metric for the capability of a discrete graphics processor. And that's been going up at a steady exponential rate as well, with empirical dots shown. Now, a lot of people have been spending a lot more time at home looking for ways to fill the time, and gaming has exploded accordingly. And billions of dollars are in esports, and people are looking for a more immersive gaming experience. And these additional flops enable smoother frame rates, much greater detail, things like real-time ray tracing for lighting, as well as smarter non-player characters through AI innovations. So all of these improvements in the quality of the gaming experience tend to just drive an appetite for more, and we really are on the path to continue this exponential trend because the worldwide demand is inexorable. And having mentioned AI, I need to show this trend, which dwarfs all the others, where the doubling rates over time are measured in months, not years. And this is driven by the growth in the accuracy of these models, which is tied to the number of parameters in the models themselves. The parameters enable compelling applications of natural language processing, image recognition, sophisticated recommendation systems for all kinds of corporate applications and personal quality of life benefits. To get that level of accuracy, we need billions and even trillions of parameters, and that drives a tremendous thirst for compute to actually train those networks. So that's why we see this huge increase in compute demand from machine learning. So this is all compounding together to create a world where computation is in short supply. All of these things are benefiting people's lives and whetting their appetite for more. Now to the more sobering aspect. So that's a bright future of compute and compute demand, but we have some sobering trends. And this graph here is based on some work done by the Semiconductor Research Council last year, plotting the energy consumption worldwide of the amount of computations per year. And as with the compute demand trends, this is on an exponential growth path. And in fact, projected out over a decade, it starts to consume a very sizable portion of worldwide energy production. And we, of course, want our energy consumption to go the other direction. And so this points out that we need new approaches to have a sustainable way of delivering that compute capability within our energy constraints. To underscore why new approaches are required, another bit of work done by the SRC produced a fascinating chart, which is an empirical plot, just measured data of general purpose CPUs. And the bits switched is on the x-axis, a proxy for the energy consumed. The work done is on the y-axis. And it follows a very nice logarithmic curve. This is a log-log plot. And what it shows is that doing more work, higher performance processors, requires an exponential number of bits switched. We lose efficiency with the higher performance. And this isn't a theory, this is just an empirical observation, but it's certainly held true over time. Now, if we had perfect one-to-one efficiency in work done versus bits switched, which would be the ideal case, we would be in a very different curve that would have over 1 million times better energy efficiency than the general purpose CPU. So clearly, general purpose CPUs are not going to be adequate to meet the explosion in compute demand of the future. We need new approaches. So those are some of the headwinds, and a further dark cloud is around the much discussed slowing of Moore's law, the cracks in the law. We know that the nodes are being introduced at a slower pace and that they are delivering less with each generation. To compound that challenge, we've got the higher cost per millimeter squared of these nodes. And this isn't just the inflationary pressures that we're all experiencing and greedy semiconductor foundries. These are driven by real fundamental physics of the processing. So there are many more mask layers, much finer grain lithography required, many more materials to do these next generation complex nodes. So the increasing cost trend is certainly not going to be rolling off in the foreseeable future, which is particularly problematic because our industry has been depending on more transistors to deliver more performance with each technology node without breaking the product cost requirements. To make this even more difficult, we're seeing that at the SoC level, our IP is scaling at different rates. Logic scaling is actually still doing pretty well into the more advanced nodes, but SRAM is falling off the curve, and analog devices fell off the curve a long time ago and are getting very small shrink rates with each node generation. So that means that when we roll it up at the SoC level, we see a significant flattening in the device and the overall SoC scaling. Sure, we get more gates per millimeter squared, but those occupy a diminishing fraction of an SoC, and most of the SoC is consumed by the poorly scaling analog interfaces and required embedded memory. So these trends support a need for new approaches to deal with the physics and the challenges of device scaling. And those challenges are going to have to be met with new approaches. And as I showed before, you look at the general purpose CPU trends on the left. The demand is unabated. We have very well-founded requirements for continuing to drive that curve up and to the right, but the energy and other factors are just going to make that unsustainable. So if you look on the right, the number of bits switched per year to get the compute requirements accomplished needs to roll over. Now, GPU accelerators have been a good, promising start in this direction. The parallel data paths and the efficiencies gained from that architectural approach enable them to apply to high-performance computing and machine learning workloads quite effectively. It's not rolling off nearly fast enough, though, to deal with the overall trends that we've seen, and we're going to need new domain-specific architecture approaches that approach that million times efficiency that I showed you in the general purpose CPU empirical chart. We're going to need to find ways to deploy these domain-specific accelerators and design them into existing products. So the domain-specific world is already well underway, and we see those with all kinds of accelerators in smartphones, laptops, and other SoCs for video, audio, and such processing. But even in the general purpose domain, AMD has taken a step in this direction with our GPU architectures. So GPUs have been shown to be more efficient at certain forms of computation than CPUs. And we've even bifurcated now the GPUs into domain-specific architectures. The red on the left being our Radeon gaming optimized line, and the blue on the right being the compute optimized line, we term CDNA. And the reason we did this and get significant benefit is, if you think about it, the compute side of the world, it needs lots of math, 16-bit math, 8-bit integers, 64-bit floating point to drive the HPC and the machine learning and all those things. Nobody who's running those workloads wants to be rendering pixels, doing ray tracing and texture processing. So all of that gaming-oriented circuitry is just overhead. And by removing that and focusing just on math, we can get a much more efficient architecture. Similarly, on the gaming side, we don't need the high rates of FP64 throughput. We don't need all of the math capabilities. We need just what's necessary for gaming. So partitioning this big market into two dedicated, more efficient architectures has proven quite successful. But if we extend this trend arbitrarily far and start providing very specific architectures for every possible market, we end up with an unsustainable design burden on our teams. And so we need a smarter approach. And the big question we have to answer is, given the headwinds here of the physics slowdown, physics impacts to our device scaling, and the challenges of meeting the compute demands, how are we going to architect, design, and build these future systems? These systems have to be far more efficient than the ones of the past, more flexible, and that's what leads to the fundamental architectures in the coming years are going to be modular in nature. We need to be able to mix and match capable accelerators for specific markets, and we need to be able to assemble them in an efficient manner. And there's a lot of technology innovation required to achieve that vision. So let me run through a little bit of the technology underpinnings that are necessary to get to that modular design vision. And I'll start with the basics of chiplets. So chiplets are much talked about now. We, as AMD, we really started this architectural direction back in 2019 with our EPYC and Ryzen lines. And one of the main motivations there was related to yield improvements. And it can be visualized here. You know, back in the good old days of the Moore's Law gravy train, we would get twice as many transistors in a given millimeter squared, and that could provide the performance improvements, the feature sets required for the next upgrade cycle. The current trends don't support that kind of a doubling, and we have been bloating out our high performance processor designs generationally on an unsustainable trend. The die sizes growing up towards the reticle limit, and that's become economically non-viable. So what we've started doing is splitting what architecturally looks like a monolithic SoC into 2 or more chiplet subcomponents, as shown here. Now, those 2 X's shown actually are bigger than the single monolithic because they need to contain overhead to not only talk to each other with an interface, but to be tested in a standalone manner, to have their own power management, thermal sensing, all the other aspects that a standalone chip requires. So they aren't free, and they are more complex to architect because we have to partition that source SoC at boundaries that conform to the limitations of the chiplet interconnect technology. And that's a very key aspect I'll spend a little time on. We need to have methodologies and architectures that work together to provide an optimal chiplet design. The next key benefit of chiplet architecture to highlight is the yield improvement one. And this is mentioned in passing often, but to illustrate it here, it becomes really clear if you envision a starting wafer as a collection of die that have a fixed number of defects on them. We don't have perfect manufacturing processes, we have defect densities. And so if you have very large SoCs, which is what we've been designing of late, and a fixed number of defects on the wafer, that takes out a set of these large chips, and you can build a certain number of functional SoCs. If we subdivide that large SoC into, say, 4 smaller chiplets, put those on the same wafer, you have the same number of defects, it takes out now just one of these little chiplets, and the remaining good chiplets can be tested and assembled into a much larger number of fully functional SoC equivalents. Architecturally, these things look like a monolithic SoC if we've done it right, and we end up with a lot more product. We can also mix and match numbers of chiplets to scale up and down the market. So many benefits from this approach, and perhaps a less obvious one illustrated here with these red die is that we can cherry pick faster chiplets, and if we have the right test analysis and speed binning processes, we can put those onto premium parts for customers who are willing to pay more for the absolute maximum performance. So many compounded benefits from this kind of a chiplet architecture. But we need a lot more than just yield improvements. We need to deal with all of that energy challenge and meeting the compute demand with more domain-specific architectures. And so from our modular approach, we need to be able to mix and match different types of chiplets together in mixes appropriate for target markets. Because one of the big problems, like I mentioned before, we are specializing our architecture because that's the only way to meet the compute demand, the only way to get the efficiencies of compute. So we end up targeting smaller and smaller market segments. In order to do that in an economically viable manner within engineering resource constraints, we have to be able to design these subcomponents that can be mixed in different balances to meet new markets. And that's where the true strength of modular design comes into play. So we have domain-specific accelerators. We can include 1, 2, or 4 of those, depending on the market demand, and the general purpose CPU can comprise whatever subset of the product cost that we want to allocate to it. That is the real flexibility benefit of modular design. So I've mentioned that chiplet interconnect overhead is significant, and we need to be able to co-design our package architecture to the demands of our chiplet modules. And there is truly a smorgasbord of package options out there, and the challenge is which to select. The industry, AMD and many others have been doing MCMs for many years, and these are very cost effective and have solved a lot of product design challenges. There have also been high volume production, and very much so today, in these info processes that use RDL metals in a module to build up the interconnect between die. We also have passive silicon interconnect package technologies, things like EMIB silicon interposers, where we have a 2.5D implementation with a passive silicon layer that provides the wires to connect up the die. And then there are the 3D approaches, many of them in production today, things like Intel's microbumped Foveros, but also things like on the bottom right, wafer on wafer for image sensor processors and memory chips that are in production today. So this is a dizzying array of package technologies that all have their own merits, pluses and minuses. And choosing the right one is one of the big challenges all of us in the industry are going to face in the coming years, making this a new frontier of multidisciplinary innovation that is going to span silicon architecture and package technology. So to illustrate one of the metrics that we use for this package selection, I've plotted here just couple of the package technologies on two axes. The axis on the left is the linear interconnect density. So you can think of that as the amount of beachfront that a die requires to communicate a certain bandwidth to another die. Wires per millimeter per layer. And MCM's, of course, lower, and we move up and to the right. The areal density is the axis on the right in orange, which is the number of interconnects per millimeter squared. And that is particularly critical when we start getting to 2.5D and 3D approaches. Clearly, the capabilities of the MCM are the starting point in the chiplet revolution, and it's worked out well for AMD because we architecturally partitioned our design in such a way that linear bandwidth density was sufficient for our needs. We put the CPU cores with their L3 cache on one chiplet, and the other chiplet had the memory interface and the off-package I/O interfaces. The CPU to memory bandwidth requirements are sufficiently modest that with a carefully crafted SerDes interface on package on organic interconnects, we kept the power and the area overheads low enough that it worked well. But as we move to more demanding applications with higher bandwidth requirements, we need new approaches. We quickly burn too much power in those on-package SerDes or take too much area for them. So in the middle there, we have a 2.5D silicon interposer. That's one of our Instinct processors. The four little die on the periphery are the high bandwidth memory. High bandwidth memory is high bandwidth, and in this particular design, we generate more than a terabyte of bandwidth to the GPU compute engine in the middle. And that requires a more advanced package technology than MCM. And in this case, we've used both silicon interposers and more recently our elevated fan-out bridge approach, which I'll talk a bit more about. But it is meant to be just supplying the required bandwidth with the minimum amount of area overhead. Then as we move to the compelling 3D approaches on the top right, this is where we have new opportunities for architectural partitioning, and in this case, that 3D stacked die is an L3 cache chiplet that amplifies the amount of cache storage in the CPUs and provides very compelling uplifts. But in order to do that, we need to support thousands of signals between these die at very low energy and at very low area for it to be practical. That's why 3D is so compelling. So putting this together into a kind of a high-level trade-off view, finding the optimal solution is an iterative process. It's a multidisciplinary design challenge where package engineers, computer architects, and circuit designers of all disciplines have to work together towards the right balance. And shown here, as we move from the less dense to the more dense package technologies, the costs go up. There's a package cost adder to deal with. Organic MCMs are nice and cheap, but they don't have as high bandwidth density. The silicon interposer is definitely more expensive and improves on that. 3D, of course, requires a lot more processing steps, a lot more fine-grained lithographic processing equipment to implement it. So it's by nature more expensive. But the efficiency goes up. And choosing the right balance involves solving an equation, something like this, where we need to deliver more value than the cost overheads. If you look on the right, the chiplet die overhead adder, well, the amount of area for these interfaces is going to eat into that yield benefit I went through that looks so good at the outset, but can start to erode quickly if the interface gets too big. The package cost is just an additional overhead. So if we have to add a silicon interposer, that's cost that we didn't have before we split the die into chiplets. Then there's the power cost of the interconnect. All of our designs are power limited today, and any power spent, additional power talking die to die, eats into our performance. And finally, we can't ignore the engineering complexity factor at the bottom. We only have so many talented engineers in the world. Every company is limited in that regard. It's a constant point of stress, and designing these stacked multi-die chiplet solutions is just more complicated. You have two pieces of silicon, you have a new interface, you have to solve all of the latency implications and thermal implications. So it's often a tripping point is we can have the elegant, architecturally perfect solution, but we can't execute it on the product refresh cycle time. So all of these things have to be analyzed together to determine what the optimal solution is, and it becomes a very multidisciplinary, challenging problem. But it's why our jobs are going to continue to be fun. And to show one of the outcomes of that iterative process, I'll highlight here what we have termed the elevated fan-out bridge solution that we deployed on our MI200 Instinct supercomputing processor, which was just announced last month. And we used a new approach that's shown on the right, which improves on an already existing industry solution that uses an embedded interconnect bridge on the left. Now, there was a good reason to do the design on the left because it improved upon the silicon interposer substrate that has been used in the past to connect to two die or HBM together. This doesn't require TSVs, so the electricals are better, and it's a small, scalable solution. But it comes with downsides in that a cavity has to be dug into the package substrate to house the silicon interconnect bridge, and we need significant placement accuracy, improvements in the assembly process to connect to those microbumps in the embedded bridge. By going to the elevated bridge approach on the right, we get the benefits of that embedded bridge in that it improves on the silicon interposer, but we don't have to dig a cavity in the package, and we can use a lithographically defined patterning approach to assemble the module before attaching it to the organic package. So we end up with improved tolerances and placement accuracy. So this is just one of the evolutionary refinements in package technology as we press on the stress points of that complex optimization equation I showed before. And putting that together, showing the AMD, the Instinct design here, these chiplet architectures are complicated. There are a lot of pieces to put together. And it takes more engineering than the simple monolithic design did in the past for the assembly, and more on the packaging and the manufacturing side as well. We have two compute chiplets connected together with 8 HBMs and the associated EFB silicon bridges to connect them together. And done right, we can keep the complexity contained and still provide all the cost and the modularity benefits that we are after. So I want to spend a little more time now on 3D, which is the perhaps holy grail of chiplet and modular architecture done right. And in particular, the hybrid bond approach that we have unveiled with the V-cache designs for both our server and desktop lines has some extremely compelling properties. So hybrid bonding is called hybrid because it's a two-step process. We take two pieces of silicon and polish them in a clean room process. Hydrophilic silicon dioxide bonds are then mated together in an annealing step. So we generate a chemical bond between these two pieces of silicon, after which they are mechanically as solid as a single piece of silicon. And embedded in each of those pieces of silicon are buried copper plugs. And the same or a second annealing step can cause that copper to expand and then generate a metallurgical bond between those copper pads. So we end up with an electrical connection and a mechanical connection. And out of that result, we end up with a very finely patterned, very mechanically sound stack of two pieces of silicon. And this has been in development for many, many years. And while it looks simple here, there are many challenges along the way, and it took many years of innovation, both architecturally and with TSMC on the physics side, to get this right. But having spent that time, we've gotten quite a compelling result. And there's several non-obvious benefits here that I want to point out. And there's the big numbers. You know, we got dramatic improvements in interconnect density, like I went through on that plot, right? So we know we can get a lot more signals per millimeter squared. It takes a lot less energy to wiggle those signals. But at the same time, it provided an opportunity for architectural innovations. And if you look at the chiplet on the right, what we did is we have 32 megabytes of cache in the base CCD design, and we've been selling those by the millions, right? So we got 32 megabytes of L3 cache. Now we're stacking an additional 64 megabytes with this 3D stack chiplet on top of it. So the first thing you might wonder is, how did we get 64 megabytes into the area of 32 megabytes in the original design? Well, that's because this V-cache chiplet's only purpose in life is to provide dense SRAM. It's not doing anything else. It doesn't have the wires to deliver the output of the bit cells to the CPU cores. It doesn't have the control to manage where the data goes. All of that stuff lives in the base CCD. This chiplet is just providing a huge sea of SRAM, and those bits are then shuttled around on the base die. So it can be a lot more dense. If we had to implement that chiplet in a planar thing, let's say we could say, let's instead triple our cache with just a planar design. Well, we wouldn't get those density benefits. It would have the same density as the existing 3D cache, and it would be twice as big. And we wouldn't have room for those chiplets on the package. And in addition, because it would now be such a big sea of SRAM with all of the wires and control necessary to drive it, the latency would go up very significantly. So we'd end up with a slower, higher power, less dense version of this. So the 3D stacking not only enabled the opportunity to architecturally differentiate and provide much higher performance with this triple cache, but in a way that would be completely inaccessible with legacy 2D approaches. We have a density optimized chiplet. All we have to do is hop up and down 10 microns across TSVs to access it, negligible latency penalty, and it acts just like it was a magically 3x more dense SRAM on the base die. So this is just a teaser for the opportunities of 3D stacking in the future. And this is why we continue and have continued to innovate in the package space. We've been doing this for a long time. Many other companies have as well, but we led the way with 2.5D HBM, provided a lot of learnings for us in this space, and enabled us to optimize for future capabilities. The MCM came around with our Naples design in 2017, where we split that die up into 4 pieces, got a lot of benefits from that. Then we had true heterogeneous chiplets with Rome and Ryzen. And now we have moved into the 3D stacking and significant refinements on the 2.5D approach with elevated fan-out bridge. So These are the starting steps in what will be a many-year, multi-decade advance in package technology, an iterative approach optimizing the architecture, package, and circuit design space. So where does the future go? We've gotten tremendous nonlinear benefits with today's 9-micron TSV pitch hybrid bond solution. The properly architected, we get the benefits I went through. Now we have industry plans for much tighter TSV pitches. So we've started with that relatively simple SRAM on CPU. We can envision things where we stack logic on logic. As the pitches get tighter, we can do more and more disruptive and interesting approaches with this very fine-grained interconnect capability. We can envision stacking different sizes of caches at a finer grain level. If you remember back, I showed SRAMs are definitely not scaling at the rate of logic. So we don't want to spend our most expensive millimeter squared of advanced technology on things that aren't scaling well. If we can put those in an N-1 node, it could provide tremendous value. Oh, and we want modular accelerators that provide domain-specific workload benefits. Maybe we can have those in a separate piece of silicon, connected or deployed in varying numbers based upon the market. And if we have a low enough overhead interconnect, that's when it becomes viable, because then we're not breaking that benefit equation and adding too much area to connect these things, adding too much power to connect these things. So this is a very rich field of research, and we have exciting opportunities ahead in this space. Now, not to sugarcoat all of this and say it's bright and optimistic for the future, we've got a lot of engineering challenges, which is why we all get paid. And the first, I'll just outline a few of those. And these, some of them aren't new, but they are becoming a lot more demanding. Test and known good die with chiplet architecture, that's a well-known challenge. So now we're taking all of these disparate chips and putting them together and building up these very expensive complex modules. If any one of those die is bad, we might have have to throw away the whole module. And that's not economically feasible. So we need better test approaches, and we want to be able to mix and match the fast parts with fast parts, slow parts with slow parts, or else we end up selling processors that are all as slow as the weakest chip in the link, which isn't great. So advances in test and KGD are critical. The other big one that I'm excited to see new innovations in are around thermals. So this stacking approach is going to increase power density. There's no two ways about it. Now, if you are thinking about the way we architected that V-cache design, you might notice that we stacked cache on top of cache. The CPU cores on the left and right side of that chiplet, they generate the most heat, of course. The caches are low power density. So we didn't stack cache on top of the hot CPU cores. We kept the cache together, and we put just dummy silicon on top of the CPUs so that their heat could go out the top. Well, as we start to get more aggressive in our 3D stacking and logic on logic and other approaches, the thermal problem is going to get much more challenging. So we need better heat dissipation, heat removal technologies. We need more advanced power management that can locally mitigate these problems. And it's going to be an area with a lot of development. Power delivery as well is always a challenge, but it's made much more significant with 3D stack. Now we have these skinny little TSVs delivering power up to die on top, as well as to the die on the bottom. And there's IR drop, there's all of the things to go along. So we've got to bring to bear all of our linear regulator, integrated voltage regulator approaches to manage these things and to model these things in a third dimension, which from a EDA perspective is a whole new challenge. And finally, I should mention the system level integration. I mean, we're delivering more and more of our value at the system level architecture with the software wrapped around it. So all of these things need to be tied together to generate that system level scaling, because the performance isn't going to come just within the silicon. Silicon scaling is slowing down no matter how much we do with chiplets, and we're going to meet that compute demand at the system level in the future. So the road ahead is exciting. Tons of opportunities for rapid innovation across many different disciplines. It's a richer space for finding exciting solutions that take parts and pieces from package technology, circuit, system architecture, silicon design, put them together in disruptive ways to generate true major value in the market that our customers in the world is demanding. The economics are clear. Chiplets are the future. Modular design is the future. Domain-specific accelerators are going to be required. The companies that make the most of putting these together in flexible, market-specific ways are going to win. And it's going to be a very exciting future with innovative products and exciting new technologies as we go forward. So that concludes my talk, and I've got a few minutes left to take some questions. Yep, mic right there.
Actually, I have two questions. Thank you very much. Very nice presentation. You talk a lot about packaging and 3D packaging. What is your views that the packaging and the design done in a simultaneous way, usually with the way the tradition we have done it, is we do the design, we go to the OSAT, we give the packaging, then there is an iterative process until the things get right. Now, in order to do this, we have developed the PDKs for the design, but we need something equivalent, for packaging, so you have a concurrent use during the design phase. So what are your views on this concurrent co-design type of an approach?
Yeah, and that's been a cultural change that we've been building inside of our company, at least, where the packaging, we used to have very separate teams, and the package design rules were fixed, and we do our SoC design, we'd throw it over the wall to the package teams, and they would figure out how to yield the package and make it work. And we would be very slow evolution of the design rules. Now we're pushing those design rules to the limit, and we're having to optimize that equation I showed. So we have the package. Well, first of all, we've had to invest a lot more in package technology development, both internally and with our OSAT partners and foundry partners. And secondly, those folks are now a part of our architecture teams. So they are embedded in our early concept design phases, working with us on the possibilities to make the best product. And so they come up with ideas on what the package capabilities could be in the future. And we work on what that means for a better architected solution. So it's expanded the disciplines involved in our early architecture exploration phases.
Hi, I have a question about the test and known good die, specifically for 3D chiplets. And one of the benefits you did say, like for chiplet, you can kind of like pick and choose good dies and even better dies, put them together. But 3D, my question is, if you try to probe the dies, either you leave the oxide or even leave a probe mark, that could kind of hurt your yield of the hybrid bonding process. How are you guys getting around that problem?
Yeah, I can't reveal too much about our secret sauce there, but we do have a limited number of pads that we dedicate, sacrificial pads, to test access points at wafer sort. Yeah. The performance cost ratio of planar versus 3D. That's a tough one to answer because as I mentioned, we get these nonlinear benefits with a properly architected 3D solution. So things that just couldn't be done in 2D, we can do with 3D and deliver a lot more performance. It comes with a cost. So at the end of the day, it's market driven, right? If customers are willing to pay for that much better performance, that better architecture that 3D enables, then it's worth doing and compelling. And that's what we've observed. And then I show the yield equation of taking a big die and splitting it into smaller ones. You get a lot more good product out of the result. Well, if you take those smaller die and split them again and try to improve the yield, well, you're really at diminishing returns at that point, right? Because now you've got to add more, the fraction of overhead for chiplet connectivity is higher and your yield improvement is less. So there's kind of a sweet spot for chiplet design size. One more.
Hi. So what kind of software or hardware support you added to support for the 3D Vcache die? So I guess, yep. So I guess you have this
to exploit it architecturally with software.
Yep.
Well, that was one of the big attractions and why this was a perfect first vehicle for 3D, because cache size is already a configurable parameter in our designs. We have 1 megabyte per core, 2 megabyte, 4 megabyte per core. This goes up to 12 megabytes per core, and the software really doesn't care. It's a hardware managed cache, so demand based, and yeah, so it's actually completely transparent. Now there are software optimizations where they can factor algorithms so that it's cache resident. So some customers would be taking advantage of that, but to a first order, it's not software visible. Appreciate the questions and the opportunity to speak to you all. Thank you.